Hi, hello, this is Giri, teaching 10th Mathematics, the chapter Real Numbers. Here is the alternative academic calendar second week work. Now, this is the 4 weeks schedule for 10th Mathematics, out of which we already completed the first week syllabus. Now, this video is on second week work. Look at the second week syllabus. First point, the statements of the definitions and theorems in the chapter need to be discussed. The second point, the proofs of the theorems should be discussed. Students should try to send their views and analysis. Now, in this video, let us look at the first theorem of this chapter, which is Euclids division lemma. Let us know the statement of this Euclids division lemma. The statement is, given positive integers a and b, then there exists a unique pair of integers q and r satisfying a is equal to bq plus r, where r is greater than or equal to 0 but less than b. This is the statement of Euclid's division lemma. I shall repeat. Given positive integers a and b, then there exists a unique pair of integers q and r satisfying a is equal to bq plus r, where r is greater than or equal to 0 and but less than b. Now let us try to understand this division lemma with a simple example. For example, if we divide 7 with 2, then you can write 7 as 2 times of 3 plus 1, isn't it? You see, look at this. Look at this division. Here this is the division. If we divide 7 with 2, this 2 in 7 3 times, 3, 2, 6, and if you subtract 6 from 7, you will get 1. Now this is dividend, 7 is the dividend, and 2 is the divisor, 3 is the quotient, and 1 is the remainder. Good. Now you can write this 7 as the product of 2 and 3 plus the remainder 1. This is division rule. Dividend is equal to divisor into quotient plus remainder. Therefore, you can write 7 as 2 into 3 plus 1. You see, if we divide 7 with 2, then 7 is equal to 2 times of 3 plus 1. The remainder should always be either 0 or less than the divisor. Here, if we divide this number with 2, the remainder should not be 2. It should be less than 2. Similarly, if we divide this number with 3, the remainder should be either 0, 1 or 2. Since we are dividing this 7 with 2, this 7 is equal to 2 times of 3 plus 1, and this 1 means remainder should be greater than or equal to 0 but less than the divisor 2. This is the Euclid's division lemma. Now, here if you look at the statement, there are two integers a and b, where a is greater than b. Since a is greater than b, you can divide a with b. If you divide a with b, then there may be some quotient. Let us name the quotient as q. And there may be some remainder. Let us take the remainder as r. Now if you divide a with b, then b in a quotient times. And if you get the quotient, then you have to multiply these two. B into q is bq. And if you subtract bq from the dividend a, you will get r. So that you can write the a value as b into q plus remainder r. You see, a is equal to bq plus r. Here the remainder should be, here what is the remainder in this case? The remainder is r. Therefore the remainder should be greater than or equal to 0, but it should be less than b, less than the divisor. To compare this with this given example, so that you can understand very easily. You see, the statement is, given positive integers a and b, then there exists an unique pair of integers q and r satisfying that a is equal to bq plus r, where r is greater than or equal to 0 but less than b. How can you understand this? By taking 7 and 2. If you divide 7 with 2, this 2 in 7 3 times, 3, 2, 6, and the remainder is 1. Therefore, you can write 7 as 2 times of 3 plus 1. You can write 7 as 2 times of 3 plus 1. where the remainder 1 is greater than or equal to 0 but less than the divisor 2. Similarly, if we divide a with b, there are two integers a and b. If we divide a with b, then there is some coefficient q and the remainder is r. Therefore, you can write this a by using division rule as a is equal to b into q plus r. If you go for any division, either the remainder is 0 or the remainder may be positive value and it should be less than this divisor. Therefore, r should be greater than or equal to 0 but less than b. This is Euclid's division lemma. Now, let us find the HCF of 50 and 70 using Euclid's division lemma. It is a very important model as far as the public exams are concerned. Look at the question again. Find the HCF of 50 and 70 using Euclid's division lemma. HCF is also called GCD. You may please keep in mind. HCF means highest common factor and GCD means greatest common divisor. Factor and divisor are both same. Highest common factor is HCF. GCD means greatest common divisor. Both are same. Find the HCF of 50 and 70 using Euclid's division lemma. Here is the solution. Now let us write the statement of the division lemma first of all. Given positive integers a and b, then there is an unique pair of integers q and r satisfying a is equal to bq plus r, where 0 is less than or equal to r is less than b. Now, using division rule, out of 50 and 70, we have given two numbers 50 and 70 now. Out of these numbers 50 and 70, the biggest number is 70. Now we have to divide this 70 with 50. Now this 50 in 70 one time. Therefore 70 is equal to 1 time of 50. What is 1 into 50 is 50. Now if you subtract 50 from 70, you will get 20. Therefore the remainder is 20. 70 can be written as 50 times of 1 plus 20. Here a is equal to 70, b is equal to 50 and q is equal to coefficient is 1 and the remainder is 20. Here the remainder is not 0. We have to do this same division rule till you get the remainder 0. Now in the first case you took 70 and 50. And in the next case, we have to consider the divisor and the remainder in all the steps. Now you consider 50 and 20 now. Out of 50 and 20, 50 is greater than 20. Therefore, divide 50 with 20. Now you can write 50 as 2 times of 20. What is 2 times of 20? 40. And what is the remainder? 10. Therefore, 50 is equal to 20 into 2 plus 10. Here a is equal to 50, a is equal to 50 and b is equal to 20, q coefficient is 2 and the remainder is 10. Again the remainder is not 0. Since the remainder is not 0, again you have to go for the next step where you have to consider the b value and the remainder. You have to consider the divisor and the remainder. Divisor is 20 and the remainder is 10. Now consider 20 and 10. Now if you divide 20 with 10, you can write 20 is equal to 2 times of 10 plus 0. Here you get the remainder 0. Since the remainder is 0, in this case, what is the divisor? At the step of getting 0 in the remainder place, what is the divisor? Divisor is 10. Since the divisor is 10, the HCF of 50 and 70 is equal to 10. In this process, you have to find the HCF of two numbers using Euclid's division lemma. Now you see here it is the fundamental theorem of arithmetic. Let us see its statement. The fundamental theorem of arithmetic states that every composite number can be expressed as a product of prime factors in a unique way. I shall repeat, every composite number can be expressed as a product of prime factors in a unique way. Means in only one single way. Unique means in only one way. You may try to understand. First of all, what is a composite number? Composite numbers means a number which is having more than 2 factors is called composite number. A number with exactly 2 factors is called prime number, and a number which is having more than 2 factors is called composite number. Now every composite number can be expressed as product of prime factors in only one way. Now let us try to understand this statement with a given example. Now if you look at this example 30, you can write 30 as 2 into 3 into 5. 2, 3, 6, 6, 5 is 30. You see, you can write 30 as the product of 3 prime numbers. 2 is a prime number, 3 is a prime number, and 5 is a prime number. You can write 30 in only in this way, and you cannot write 30 in any other way as the product of prime numbers only. Of course, you can write 30 as 6 into 5, but 6 is not a prime number. Therefore, you can write 30 as the product of prime numbers in only one way, and there is no other way. Similarly, look at 36. You can write 36 as 4 into 9. This 4 is 2 into 2, and this 9 is 3 into 3. 2 into 2 is 2 square, and 3 into 3 is 3 square. Therefore, you can write 36 as 2 square into 3 square. You can write 36 as the product of prime numbers in only one way. Similarly, 60. 60 is nothing but 4 times of 15. 4 is 2 square, and 15 is 3 into 5. Therefore, 60 can be written as 2 square into 3 into 5. This is the only one way in which 60 can be written as the product of prime numbers. This is called fundamental theorem of arithmetic. Every composite number can be expressed as the product of prime factors in a unique way. Now go for another example, 420. This 420 you can write it as 2 into 210. Again you can split 210 as 2 into 55, and you can split this 55 as 5 into 11. Therefore, finally 420 is equal to 2 into 2 into 5 into 11. 2 into 2 is 2 square into 5 into 11. Therefore, 420 can be written as the product of prime factors as 2 square into 5 into 11. This is again an unique way. This is what is fundamental theorem of arithmetic. Note, writing any composite number in this form is called exponential form or prime factorization method. You see, you wrote 30 as 2 into 3 into 5, and you wrote 36 as 2 square into 3 square. You wrote 60 as 2 square into 3 into 5. We wrote 420 as 2 square into 5 into 11. All these numbers can be written as the product of prime numbers. This type of writing all these numbers is called exponential form, and the method is called prime factorization method. The next concept is HCF and LCM. HCF stands for highest common factor, and LCM stands for least common multiple. You come across what is HCF and what is LCM in your previous classes. Now here is a question. Find HCF and LCM of the numbers 60 and 75 using prime factorization. I shall repeat. Find HCF and LCM of 60 and 75 using prime factorization. Here is the solution. First of all, write 60 as the product of prime factors. 60 is nothing but 2 into 30. Again 2 into 2 into 30 is 15. Again 15 is 3 into 5. Therefore, 60 is 2 square into 3 into 5. And the second number is 75. 75 can be written as 3 into 25. This 25 can be written as 5 into 5. Therefore, finally 75 is equal to 3 into 5 square. Now we wrote the factors of 60 as 2 square into 3 into 5, and we wrote the factors of 75 as 3 into 5 square. Now we have to find the HCF. HCF means it is the product of common factors with their respective least exponents. Here HCF is nothing but the product of common factors with their respective least exponents. We look at these two products. Here what are the common factors you pick up? Here the factor is 2, but there is no 2 in 75. Here is a factor 3 in 60. 3 is also a factor of 75. Therefore, HCF is equal to 3 into. Here 5 is a factor of 60 and 5 square is a factor of 75. Therefore, which is common? 5 and 5 square, the common is 5. Otherwise, now out of these common factors, here the exponent is 1. Here the exponent of 5 is 2. Therefore, what is the least exponent? 1. Therefore, you have to consider 5 only. HCF is 3 into 5. These are common factors in both 60 and 75. What is the product of 3 into 5? 3 into 5 is 15. Therefore, HCF of 60 and 75 is equal to 15. HCF is nothing but the product of common factors with their respective least exponents. Now let us find LCM. In finding LCM, we have to consider the product of different factors with their respective highest exponents. In the previous case, we took common factors and we took the least exponents. And in finding LCM, we have to take all different factors with their highest exponents. You see, here 2 is a factor, but here there is no 2. Even though there is no 2 in 75, you have to take this 2 square to find LCM. The highest power of 2 here is 2 and here the highest exponent of 2 is 0. Therefore, you have to consider 2 square. Here we have 3. Here also 3. Therefore, take 3. Here we have 5. But here 5 square. What is the highest power? 5 square. Therefore, take 5 square. And you find the product of all these. 2 square is 4. And this is 3. 5 square is 25. 4 into 3 into 25. 425 is 100 into 3 is 300. Therefore, the product of different factors with their respective highest exponents is LCM, and the product of common factors with their respective least exponents is HCF. Hello students, so far we discussed two theorems of this chapter. The first is Euclids division lemma and the second is fundamental theorem of arithmetic. Now let us learn some more theorems. Here is another theorem. Let x be a rational number expressed as terminating decimal, then it can be written in p by q form, where p and q are co-primes and q can be expressed in the form of 2 power n into 5 power m. I shall repeat. Let x be a rational number expressed as terminating decimal, then it can be written in the form of p by q, where p, q are co-primes and q can be expressed in the form of 2 power n into 5 power m. I shall try to explain this. You may please listen carefully, dear students. Here, a rational number is expressed in terminating decimal. Means we have given a terminating decimal. We know that a terminating decimal is a rational number. Now, this terminating decimal, if we change it, if you convert it into a p by q form, if you write the given terminating decimal into a p by q form, then that q, that denominator of the fraction, should be expressed in the form of 2 power n into 5 power m. Isn't it? You see here, if a terminating decimal, a rational number is given in the form of a terminating decimal, if you convert it into a p by q form, if you convert it into a fraction form, this q means the denominator should be in the form of 2 power n into 5 power m. Look at this example, you can understand very easy now. Here is the example 0.5. 0.5 is a terminating decimal, isn't it? Terminating decimal. This decimal place terminates by 5. There is no another place. Therefore, it is 0.5, a terminating decimal. We know that it is a rational number. Now, if we convert it into a fraction, 0.5 means after point, after decimal place, there is only one place. Therefore, you can divide 5 with 10. 5 divided by 10. Since 5 divided by 10, you can cancel 5 in both numerator and denominator. If you simplify this, you will get 1 by 2. If you observe the denominator 2, here the denominator is 2. Now if you observe the denominator 2, this 2 is nothing but 2 power n. Therefore, this is in the form of 2 power n into 5 power m. Because you can write this 2 as 2 power 1 into 5 power 0. Therefore, the given denominator of the fraction is in the form of 2 power n into 5 power m. You see, if I have given a terminating decimal and if you convert it into a fractional form, if you convert it into a p by q form, then the denominator q should be in the form of 2 power n into 5 power m, which is our statement. Now look at another example, 1.23. This 1.23, if you convert it into a p by q form, as there are 2 places after decimal, you remove this decimal and write 123 and divided by, as there are 2 places after decimal, then you have to divide this 123 with 100. You see, you wrote the given terminating decimal into a p by q form. This is the simplest form. Now, if you take this denominator 100 and if you write it in the form of prime factorization, you know that 100 is nothing but 4 into 25. 4 means 2 square, 25 means 5 square. Now you see, this denominator 100 is in the form of 2 power n into 5 power m. This is in the form of 2 power n into 5 power m. And look at the third example, 12.035. This decimal ends with 5, therefore it is a terminating decimal. If we convert it into a p by q form, after decimal there are 3 places, therefore remove the decimal and write 12,035 divided by, as there are 3 places after decimal, you divide this with 1000. This is now 12,035 divided by 1000. You can cancel 5 because you see p and q should be co-primes. Means first of all, you may cancel 5 in both numerator and denominator. 5 in 12 2 times, and in 24 times, and in 3 0 times, and in 35 7 times. And in 1000, in 10 5 2 times and next 2 zeros. Therefore, if you write this in simplest form, you may get 2407 divided by 200. Here the denominator is 200. Now let us write this 200 in the form of 2 power m into 5 power n. That is, 200 may be written as 8 into 25. 8 means 2 cube and 25 is 5 square. Therefore, again the given denominator is in the form of 2 power n into 5 power m. Using all these 3 examples, if you observe these 3 examples, you understood that if the given rational number is a terminating decimal and if you convert it into a p by q form, then that denominators, here the denominator is 2, here the denominator is 100, here the denominator is 200. If you observe all these denominators, then all these denominators are in the form of 2 power n into 5 power m. That's what this theorem says. Now look at this another theorem now. Let x is equal to p by q be a rational number where q is of the form of 2 power n into 5 power m, then x is a terminating decimal. I shall repeat. Let x is equal to p by q be a rational number where q is of the form of 2 power n into 5 power m, then x is a terminating decimal. Observe, this is nothing but the converse of the previous theorem. Here, in the previously, we have given a terminating decimal and we converted into p by q form. Now, we have given the rational number in p by q form. Now, if we convert this into a fraction form, then you will get a terminating decimal, provided the condition is the q means the denominator should be in the form of 2 power n into 5 power m. Understood? Look here again. If you have given a rational number in the form of p by q in the form of a fraction, where the denominator of the fraction is in the form of 2 power n into 5 power m, if you convert this into a decimal number, you will get a terminating decimal. Look at this example. 1 by 2. 1 by 2 is the given fraction which is in the form of p by q. Here, the denominator 2 is of course in the form of 2 power n into 5 power m. Now, if you convert this into a decimal number, you will get 0.5. Is it a terminating decimal or not? Yes, it is a terminating decimal. Therefore, if I have given a rational number in the form of p by q, where q is of the form of 2 power n into 5 power m, if you convert it into a decimal number, you will get a terminating decimal. Look at the example 2. 3 divided by 50. Now, here the denominator is 50. Let us observe whether 50 is in the form of 2 power n into 5 power m or not. 50 can be written as 2 into 25. That is 2 into 25 means 5 square. This denominator is in the form of 2 power n into 5 power m. Now let us convert this into a decimal number. If we divide 3 with 50, we will get 0.06. Is it terminating? Yes, it is the n digit, therefore it is a terminating decimal. If we are given a fraction whose denominator is in the form of 2 power n into 5 power m, convert it into a decimal number, we will get a terminating decimal. And third one, 114 divided by 25. Let us multiply both numerator and denominator with 4 in order to convert it into a decimal number in simplest form. Now 4 into 114 is 456, by 4 into 25 is 100. Let us convert it into a decimal number, which is 4.56. Now if you observe the given fraction, the denominator is 25. 25 can be written as 5 square, which is in the form of 2 power n into 5 power m. Now if you convert it into a decimal number, you will get 4.56. It ends there. Therefore it is a terminating decimal. If you observe all these examples, in all these examples you have given a fraction p by q in which the denominators are in the form of 2 power n into 5 power m. If the denominator is in the form of 2 power n into 5 power m, and if we convert the given fractions into decimal numbers, we will get terminating decimals. That's what this theorem says. Now let us see another theorem now. Here is the next theorem. Let x is equal to p by q be a rational number where q is not of the form of 2 power n into 5 power m, then x is a non-terminating recurring decimal. I shall repeat. Let x is equal to p by q be a rational number where q is of the form of 2 power n into 5 power m, then x is a non-terminating recurring decimal. Previously we observed that if x is equal to p by q and q denominator is in the form of 2 power n 5 power m, then we got a terminating decimal. But here in this case, in this p by q, in this fraction p by q, q is now not in this form of 2 power n and 5 power m. Then if you convert it into a decimal number, you will get a non-terminating recurring decimal. Let us observe this example 1 by 3. Here the denominator is 3. Denominator 3 means which is not in the form of 2 power n into 5 power m. Here this 3 has neither 2 as a factor nor 5 as a factor. Therefore the denominator is not in this form of 2 power n and 5 power m. Now if you convert it into a decimal number, 0.333 and so on, it has no end. Therefore it is non-terminating. And at the same time this 3, a part of this decimal value is repeating. So it is a non-terminating recurring decimal. Now second example is 5 by 11. Here if you observe the denominator is 11. This 11 cannot be written in the form of 2 power n and 5 power m, as 11 has neither 2 as a factor nor 5 as a factor. Now if you write it in the form of a decimal number, we will get 0.454545 and so on. Therefore it is non-terminating. And at the same time this 45, this part of this decimal is repeating. Therefore it is a non-terminating recurring decimal. Now observe third example, 121 divided by 6. This 121 divided by 6. If you observe this denominator 6, 6 is not in the form of 2 power n and 5 power m, because you can write 6 as 2 into 3 but not as 2 into 5. Therefore it is also not in this form 2 power n and 5 power m. Since it is not in this form of 2 power n and 5 power m, and if you convert this into a decimal number, you will get 20.1666 and so on. This 6 is repeating. Therefore it is a non-terminating recurring decimal. If you observe all these three examples, in all these above three examples, you understood that these denominators are not in the form of 2 power n and 5 power m. If you convert all these three fractions into decimal numbers, then you will get a non-terminating recurring decimal. Now another theorem. Let p be a prime number, and if p divides a square, then p divides a. I shall repeat, if p be a prime number, if p divides a square, then p divides a. Here the condition is a is a positive integer. Okay, observe this. Here if 2 divides 16, 2 divides 16 and 2 is a prime number. 2 is a prime number, and if 2 divides 16, 16 means a square. 2 divides 16, then 2 can divide root 16. Means what is root 16? 4. You see, if 2 is a prime number and if 2 divides 16 means 4 square, then 2 can divide 4. That's what this theorem says. If p is a prime number and if p divides a square, then p divides a. If 2 is a prime number and if 2 divides 4 square, then p can divide 4. This is the example. Another example now. If 3 divides 81, here 3 is a prime number, the given number is a prime number. And then if 3 divides 81, 81 means 9 square. If 3 divides 81, then 3 can divide root 81, that is 9. Now using these two examples, we understood this theorem. So far we learned around 6 theorems. And basing on these 6 theorems, you have to solve the problems from the chapter real numbers. Okay? Thank you. Thank you, dear students.